Ian Stewart, GMAT math expert, tutor and writer, and this video is part of a series of videos I'm doing featuring high-level questions that I've designed. This video is really not meant for everyone. It's meant for test takers who have already studied the topic and who are scoring at a Q40 level or above. So if that's not you, then just bookmark this page and come back when it is. My questions, they're not modeled after published official questions. Instead, they're much more like what you'll see on test day, questions testing the same familiar GMAT concepts, but in unusual or inventive ways. And the questions are quite challenging, so don't be concerned if you find some of them difficult. To get the most out of this video, you should try each question. I'll put each on the screen for 5 seconds, so press pause. But if you get stuck, don't spend more than about 90 seconds on any one problem. So this is a circular permutations question, but it's a very unusual kind of circular permutation question. It's a circular permutation with repetition. And the formula that exists in math to solve the sort of general problem of this type is extraordinarily complicated, yet never needed on the GMAT. And if your first impulse in a question like this is to try to reproduce some formula you've memorized and plug some numbers into it, you probably haven't studied the subject in the best way for the test. The GMAT is really testing how well you can think, not how well you can memorize formulas and plug numbers into them. Here, I think the most useful thing to notice right away is the answer choices are all very small. And if the answer is no greater than 12, we can probably list all 12 possibilities if it turns out to be that large in under 2 minutes. So in any counting kind of problem, if the answers are small, don't rule out kind of enumeration, listing the possibilities as a strategy, and sometimes it might be the only viable strategy, or it might be the fastest and most convenient strategy. So let's do that here. It's a circular permutation, and in any circular permutation, it doesn't matter where you put the first thing. So let's just put one blue napkin at the top of the table. And then there really are only 4 possibilities. Going clockwise around the table, we could put both our blue napkins together, and then the remaining napkins are red. Or we could put one red napkin between our 2 blue napkins going clockwise. Then we get an arrangement like this. Or we could have 2 red napkins separating our blue napkins going clockwise around the table. Or finally we could have 3 red napkins in between our 2 blue napkins. So it might at first glance appear the answer should be 4 here. But what you might notice, 2 circular permutations are considered the same if you could rotate one and get the other. And if you just look at the 2 tables on the left side, the table at the top is the same as the table at the bottom, because rotating the bottom table just one kind of rotation clockwise, you get the table at the top. And the same is true for the tables on the right. If you just rotate that bottom table clockwise 2 spots around, you get the table at the top. So there really are only 2 different arrangements we can make of these napkins, and that's the answer. So this question combines probability and prime factorization, or number theory. And if for each question Todd can eliminate between 0 and 3 wrong answers, then for each question he'll be guessing with a probability of 1/5, 1/4, 1/3, or 1/2, depending on how many wrong answers he can eliminate. And to work out the probability that Todd answers every question correctly, we'll just be multiplying together several fractions that look like these. So for statement 1, if we prime factorize the denominator, 1800 is 2 times 900, so 4 times 450, 8 times 225. So it's 8 times 15 squared, 2 cubed, times 3 squared, times 5 squared. And now we need to think about how we might get that fraction by multiplying together several of the fractions from the list at the top of the page. And to get the 5 squared, we have no choice. We'd need to multiply 1/5 by 1/5. To get the 3 squared in the denominator, we also have no choice. We'd need to multiply 1/3 by 1/3. But to get the 2 cubed in the denominator, we might multiply 1/2 by 1/2 by 1/2, in which case we're multiplying 7 different fractions together, and there are 7 questions on the test. But we could also get the 2 cubed by multiplying 1/2 by 1/4, and then there may only be 6 questions in total on the test. So we have 2 different possible numbers for the total number of questions on the test, and statement 1 is not sufficient. Doing the same for statement 2, if we prime factorize 450, that's 2 times 225, 2 times 15 squared, 2 times 3 squared times 5 squared. And now there's only one way to get that denominator. If we multiply fractions together from the list at the top of the page, we have to multiply 1/2 by 1/3 by 1/3 by 1/5 by 1/5. So in total there are 5 questions at the end of the test. Adding on the 2 questions, we're assuming he answers correctly at the beginning. There must be 7 questions in total on the test, and statement 2 is sufficient, so the answer is B. So this might be the trickiest of the 3 questions. Here P is the probability 1 card we pick is odd, and Q is the probability that 3 cards we pick are all odd. And we want to know if Q is less than 0.5. Statement 1 tells us that Q is less than 0.7, and at first glance that might not appear to be sufficient. If all we know is that Q is less than 0.7, we certainly can't tell if it's less than 0.5. But this is a probability situation, and only very specific values of Q are even possible here, so we have to investigate further. And if we first imagine we have 9 odd-numbered cards and 1 even card, and work out the value of Q in that case, it's equal to 9/10 times 8/9 times 7/8, and if you cancel, that's just 7/10.7. So if Q is less than 0.7, that really just means that we have at most 8 odd-numbered cards in the deck and at least 2 even-numbered cards in the deck. And so if we imagine we have 8 odd-numbered cards, the most we could possibly have, and work out what Q would be in that case, we find Q is 8/10 times 7/9 times 6/8, and if you cancel the 8, that's equal to 42/90, which is less than 0.5. So the largest value Q could possibly have here is less than 0.5, and so statement 1 is true. We know Q is less than 1/2, and statement 1 is sufficient. Statement 2 at first glance might seem to be impossible. Statement 2 says Q is greater than or equal to P. But P is the probability of picking 1 odd-numbered card. Q is the probability of picking 3 odd-numbered cards in a row. It normally should be true that picking 3 odd cards in a row is much less likely than just that your first card you pick is odd. So Q could never be greater than P, that's impossible. But what can be true is that Q is exactly equal to P, and that can be true in 2 extreme situations. If every card in the deck is odd, then whether we pick 1 card or 3 cards, we're guaranteed that our cards will be odd, so Q and P can both be equal to 1. Or, if no card in the deck is odd, if every card has an even number on it, then no matter how many cards we pick, the probability we get odd cards is going to be 0. So what statement 2 tells us is that either Q is equal to 1 or Q is equal to 0. We can't tell if Q is less than 1/2, and statement 2 is not sufficient. So the answer is A. If you enjoyed these questions, I've written 4 long problem sets full of high-level questions like these, along with a set of books covering all of GMAT math that teach my conceptual approach to the test, which is perfect for high-level test takers. And if you're interested in any of that material, you can just visit my website. The link is in the description below.